of some projects and topics that's related to my group. So if you haven't been to my website yet, this is me, and this is the kind of research interest I have, and some of the projects are on these areas. Ranges from if you're interested in computer science foundations, there's automata formal languages, logic, algorithms, and semantics, those kind of topics, if you're so inclined. And also working on information retrieval as another separate topic, digital libraries, search engines, social network analysis, and content organization and presentation. Those topic areas. The third one is in the biomedical informatics. That biomedical informatics is a very broad area, and we're working on a number of topics here. Specifically, one is medical image analysis. The second is web and ontological engineering, and third is information data integration and management in the biomedical research domain. The biomedical researchers. So what I'm going to show you today is were just a number of specific things that will help you or inform you how to get started. One is actually the one is a current ongoing course I want to point your attention to, that probably some of you have seen this slide. This is a course that's currently ongoing Mondays. From 5 to 7, we're meeting in Glennon 313. There are a number of students who are just sitting in because their schedule is already full, and they don't want to commit to the full project requirements. But this is one that provides project-oriented, hands-on experience for development of complex systems that uses the web as an interface. And and we currently have 23 students, junior, senior, BSMS, and PhD, a variety of them. And for this course, and actually a number of you already registered in class from the audience here, we're trying to use the latest web development technology methodology called Ruby on Rails, one of the tools to develop highly effective, interactive, flexible applications using a number of tools, actually a number of technologies that you can see listed there. But just for highlight of some of the ongoing topics in this course, particularly, let me see if I can bring it. Well, let's see. It's either too big. It doesn't get to the center. I have to sort of move it. Okay, this way. For this course, this kind of, I want to draw your attention to some of the projects here that one can work actually within the course or outside of the course if you're interested. For example, we have where the first two is actually just try up your skills, implementation of a mastermind game as both as a standalone application and a web application. Then we can, this project is to develop a grant submission system, review system, by expanding a system that we have already implemented, but it will be expansion of the functionality of that system. That's a second possible project, and some will pick that from the class at least. This one would be slightly related, but just because of the interest and background of some of the students in the class, we want to develop a genetic program to search for a universal Turing machine. where that deciding if a Turing machine is universal or not is you cannot have an algorithm to do that. So this one is that we hand code a couple of non-universal Turing machines like 5 or 10 states. Then the idea is, can you use the genetic mutation kind of idea to mutate the encoding of possible machines, Turing machines, so that you actually get the general one, the universal Turing machine. The idea is that here this life has very humble beginning from a single cell, where how can that evolve to complex human beings like us here? And one can see from machine side, you can have a Turing machine do simple multiplication, addition, those simple things. But the universal Turing machine is very unique in that it can simulate any other Turing machine. So you have a quantum leap there, and that's what we want to try to capture. Can you search? Can you find that by simple mutations and using genetic algorithms? Then the web intelligence project is about you have a researcher, and you can Google all the information about this particular researcher, but then how important or how interdisciplinary or other characteristics of this researcher is, you can characterize by discovering the underlying social network component of this particular researcher. That's quite more informative, just looking at the list of publications and list of collaborators. But you further uncover the underlying structure of that network. And then from that, you can identify the strategic position of this particular researcher. And if we want to, so this project is to develop an automatic tool that allows you to select any particular researcher and automatically determine or discover the underlying social network structure. And finally, this is a bigger project, is to implement I2B2 system using the Ruby on Rails development environment. I2B2 is actually a clinical informatics system developed by Harvard, and it's gaining popularity, used by a number of hospitals already, and it's actually there are additional new features that's being added to the system, but the implementation is in C# and those kind of environment, and we think that using Ruby on Rails, it may give us additional benefit by doing that. So this is a list of current projects that for the specific class. If you're interested in imaging, there's this topic that you might take a look at this site, this single pixel camera, and that kind of idea, this is a very recent one, is that for most of the images you sense it, and then you compress and you transfer and then uncompress it. But why, the fact that you can compress the image without losing too much information points out the possibility that why don't you sense those in the first place, so that you don't have those redundant information, and that's what's behind this idea. We actually have a junior club that meets weekly to discuss topics on this. Okay, for those who are interested, you can search for Terence Tall single pixel camera, and you'll get to this site. And you can talk to me afterwards. Also, if you're interested in this. Lastly, if you're doing work related to any of the biomedical informatics related area, there's this Choose Ohio First program, a scholarship program that you have a flyer on the hand. The benefit, the scholarship that now it's tied to endowment. So you're going to get, so the amount will be slightly over 9,000 per year per student, okay? And this can reoccur. So each year you can be awarded that much to total. In total, half of that is coming from state. Another half is come from this James endowment, Thomas and Evelyn James endowment. And that part you can use for stipend, not just for tuition, okay? But there's a catch to this program. This is called Choose Ohio First. You must be an Ohio resident. You must be interested in and taking classes and doing some projects in biomedical informatics related areas. Okay, so, and we have some more specific, details there. You must identify a faculty mentor who is willing to supervise and meet with you on a regular basis. And there's a conference called Ohio Bioinformatics Collaborative Conference that's going to actually happen on campus in June, mid-June, that if you receive this kind of scholarship, you're encouraged to participate in that conference. And so I am out of time. And any quick question, one or two quick questions? Including overhead? There's no overhead here. This is what you get. This is the direct you get. Okay. Any questions? Okay. If not, you can Google my website and send me email and make an appointment with me if you want to discuss any of the topic further. Okay. So I pass to Darrin. Is that you? Okay. Turn this off first.
Wow.
Okay. Yeah. Okay, your turn.
My turn. How am I going to do the slideshow? Beginning. Okay. All right. So I'm going to spend the next maybe 10 minutes talk about my research area. It's always kind of awkward to switch gear, into electrical engineering after a computer science professor talk about his research. So how many of you are in electrical engineering? I just want to. Only 2. Wow. So I know Steve is like 50 years, right? So how many? Huh? 3, 4. Well, anyway, I just want to make sure that my talk is interesting and useful, right? If 90% of you guys are now in EE, then it's wasting time. Anyway, so my area is wireless microsystem research, and this is a large topic, right? It can go from system architecture, network communication, information encryption, coding, security, all the way down to device circuits, even material fabrication. So more specifically, my research theme is to focus on integrating advanced sensors, actuators, and most of these sensors, actuators are made using what we call the MEMS technology, stands for micro electromechanical system, and the low power integrated electronics at the system level to achieve autonomous sensing and wireless communication capability for a number of called critical applications. And what I mean by critical application is that whenever you do something, you must identify the technical challenge and the relevant significance. So for critical application, the technical challenge including, for example, small size, lightweight, low power, and also limited access constraint. For example, you may not be able to have the wire goes in and out of system to supply the power, energy, or getting the data you're trying to sense. So if you attend one of my seminars beginning of the semester, I think I used this slide just to give you a general flavor of type of research going on in my lab. So on the left-hand side here, these are the devices that we fabricated consisting of strain gauge sensor, and that was designed and fabricated using the microfabrication facility here on campus. And this is a project that I did in collaboration with Professor Chris Zorman and Dr. Wenko, using silicon carbide as a high temperature material to fabricate a capacitive pressure sensor that can achieve pressure sensing capability up to about 400 or 500 degrees or so. So this is the silicon-based pressure sensor, and this is silicon-based accelerometer inertial sensor that we designed and fabricated using external foundry. So all these devices are designed for specific applications. For example, the strain gauge sensor is used for sensing surface strain profile on a rotating element such as a helicopter blades, so that we can study, we'll get a better idea of the fatigue of a rotating element, so that we will know how to monitor, right, the mechanical elements, the health condition, and be able to replace some of the elements before it breaks down. And for this type of high temperature sensors, right, we put into a high temperature engine. Well, the engine is always high temperature, right? It depends on which compartment of the engine you're looking at. The temperature can go from lower end about 250 degrees C or so, all the way to about 800 degrees temperature. And this is a small pressure sensor, it's about 0.5 millimeter by 0.5 millimeter size, that we fabricated here, that's put into the body of a small laboratory animal for genetic research. This is an accelerometer that puts into, where did I put this? Or this puts into our middle ear, on the articular chain behind the tympanic membrane, so that as you're talking to a deaf person, so the eardrum will vibrate, and that will couple the mechanical vibration to the articular chain, or we call the these sort of hearing bones. So the sensor will vibrate. This accelerometer will pick the vibration signal and convert to an electrical signal, which can be used as a implantable microphone. So all of this device requires some sophisticated electronics design. If you don't have a low power integrated electronics, when you combine a sensor and all the circuits together, you will end up with just a huge size, volume, and also large power dissipation, which for certain applications becomes totally useless. And so I just give you some idea. This is the strain gauge sensing, right? High temperature pressure sensing. And one of the ongoing research project in my lab is to look at how to use radio frequency to charge up a battery that's implanted into a human bladder that can sense the pressure developed inside the bladder for patients who suffer from spinal cord injury. So therefore, they will have they suffer the urine incontinence. And one of our ongoing project that's almost sort of at the end of the finishing phase is to design and implement a implantable EMG signal that we can pick up the muscle signal from a residual leg, and use that signal and interface with external microprocessor control to achieve a much improved, they call it biomimetic performance for this prosthetic leg for soldiers coming back from the war who lost the leg due to the exposure in the battlefield. And so this is almost done, and I have one student is writing up the master thesis on this. And another project that just started in my lab a number of months ago is to look at how we can design low power, low noise sensing electronics inside a soldier's booth, so that when the soldier walk around in the battlefield, instead of having GPS connect to the satellite, but there are times that you don't want to have an active radio link to the satellite, and how that system can track the soldier position in a very accurate manner, so that as you walk, every step, the sensor is automatically correcting the drift associated with associated with the output from an inertial system, for example, 3-axis acceleration and a 3-axis rotation. So this is for the cochlear implant and a small animal implant that I discussed in my in the department seminar last month. So what's going on in my lab? I have a few projects ongoing. One is to look at the multi-channel integration for small laboratory animal physiological monitoring. We have done a lot of work for the blood pressure sensor as a sort of a standalone PhD thesis. EKG core body temperature sensor as a separate thesis. So now we are at the stage to put these things together to have a multi-channel system. And another project going on is implantable battery recharging using radio frequency powering techniques. Low power, low noise, integrated electronics for high precision navigation. And also one project that I'm interested in going on now is we call it environment energy scavenging for wireless sensors, right? If you work in this research, you will know that battery, the power is always the limiting factor, okay? And often, you know, the power source limits how much computation power, how much computation you can do, right? And how large the distance you can wirelessly transmit the information. And of course, right, anything else that's exciting to me, exciting to you, I always like to work on these things. So I guess I took less than 7 minutes. I'm ahead of schedule. I only have 4 slides. And again, I always find it difficult to come here giving a 10-15 minute slots to talk about your research, because in order to develop I call it a meaningful discussion, you and I will need to sit down and have maybe a 2-hour discussion. So when you walk out that meeting, you know something. 15 minutes is a very brief overview. So to me, whether I give you a 7 or 8 minute talk or 15-minute sort of overview does not make any difference. So if you're interested, you can always get a hold of me by email in my office in Glennon, and we can arrange a time, for further discussion. All right? So that's all I have for today.
Okay, I have got some extra time, so I'll talk about hardware security. And let me give a disclaimer. By hardware, we mean integrated circuit, integrated electronics. Now, we already know about software security. We know about software virus. We know antivirus. We know software IP protection. But what about hardware security? It turns out that it's a new topic. It's a relatively new topic. And in hardware security, we deal with security of integrated circuit. For example, the question is, can we have time bomb inside an IC? Or how do you protect the hardware intellectual property? So these are the questions we will be talking about today. But again, this is a new topic. We have started working on this very recently. And there are a lot of questions which are unanswered. And we will talk about those questions today briefly. Now, before we go into details about hardware security, let's give you an overview about our lab. The name of the lab is Nanoscape, Architecture, Circuit, and Model for Nanocomputing. So it encompasses a lot of different things, different levels of design abstractions, starting from circuit to architecture and going to computing model. So there is a website for this lab. And if you're interested, you can go into that lab. There are descriptions about research topics, recent publications, and the people involved in this lab. And of course, the main workforce for this lab are my students. Some of them are doing PhD and some of them are doing masters. So in total, we have 6 active members of this lab working in Glennon 519D. We are moving to a new lab, that's Glennon 709 shortly. And there are several sponsors for the research we are doing in this lab, starting from DARPA, Air Force Research Lab, Intel Corporation, and National Science Foundation. So this is the overview of research we are doing in this lab. The first one is low power and robust electronics. And in that, what we do, we try to reduce leakage using circuit or architecture level techniques. We do self-calibration and self-healing, because you know, if you do electronic design in nanometer devices, then there can be variations, there can be defects. So can you do healing post-fabrication so that your yield is up, so that the reliability is up? Now, the last one here is robust logic design. And again, when you go to nanoscale device, the voltage level and current level is significantly reduced. That gives to lower noise margin. So the question is, can you come up with techniques to design circuit or architecture which has higher noise margin or higher robustness of operation? The second one is nanocomputing. And I think most of you know that CMOS, conventional CMOS devices is going out of business, almost out of business in next 10 or 15 years. Now what's next? Now there will be some devices which will eventually replace CMOS and which will have higher potential in terms of computing power than CMOS, or maybe higher integration density also compared to CMOS. Now what are those devices? We don't know, but there are several candidates here right now, like carbon nanotube, like single electron transistors, quantum computing, and all those things. But if you really want to do computing with those novel devices with interesting switching behavior, you need to have new computing model, new circuits, new architecture. So we talk about that paradigm, we investigate that computing paradigm which requires significant change in terms of circuit architecture and system level design. The third one is implantable electronics. Now, Darrin talked about implantable electronics a lot in the last lecture. We will not go into details about that. My part of investigation here involves developing novel neural signal processing algorithms so that you can analyze the signals recorded from inside the brain and decode meaningful information from that system. So we develop algorithm and corresponding low power hardware for neural signal processing, which can be eventually used for closed loop neural control for prosthetic devices, which is required to enable people which are disabled due to their problem in central nervous system. And the final topic is the topic of today's talk is hardware security. And in hardware security, as I mentioned, we deal with the security or trust issues in integrated circuits. So there are 2 main topics we look into here. One is called hardware Trojan detection. And again, we know software Trojan, that's a specific virus we are talking about. But what about hardware Trojan? Can we have malicious circuits embedded inside the hardware? Can we have time bomb inside the hardware which triggers specific time during the operation and causes disruptive behavior? And the second one is protecting hardware intellectual property. As you know, today's complex integrated circuits are built with smaller modules, smaller hardware modules, which are also called intellectual property, typically bought from a third-party vendor. So these intellectual properties can themselves have Trojan. So how do you verify that? How do you verify that IPs coming from a third party are really trustable, are really trustworthy? And secondly, these hardware IPs can be hacked. A potential attacker can hack the hardware IP, reverse engineer it, and sell it or clone it as its own. So how do you prevent that? Because these are really billion-dollar property, and you need to make sure that, like the software intellectual properties, you can also protect the hardware IPs. So that's the topic. It's hardware security, an emerging challenge. We're looking into it for last 1.5 years, almost 1.5 years. So as you mentioned, if you look into an integrated circuit which can compose of millions to billions of transistors, how do you make sure that there is no malicious circuits hidden inside that? And this is a nice caricature I took from a website which says that if you take an IC, it may not be trustworthy. So your job or the job of a researcher is to make sure that we have design techniques, we have test techniques or validation techniques to make sure that the ICs which are going to the end user are trustworthy and secure. Now the question is that like software where you have passwords, you can protect everything using password. Now can you have some locking system for the ICs? Can you have a key which can be used for enabling or disabling the IC? So that's a big million-dollar question, and of course the answer is not known yet. So now what are the challenges? Now if you look into hardware design, it goes through several design phases. So first it starts from the IP vendor, and as I mentioned, these IPs are small hardware modules, and these IP vendors will sell the modules to the IC design house. The IC design house will assemble the IPs and make a complex integrated circuit design. That design is sent to fabrication facility, and inside the fabrication facility we fabricate the complex integrated circuits which you use in your system today. Now at different levels of the integrated circuit design phase, we have different security threats. For example, as I mentioned, the IP vendor can provide an IP which have inside it hardware Trojan. And by hardware Trojan, we'll give you an example shortly. We mean a small circuit which cause malicious effects into the circuit. Now that's from the IP vendor. And secondly, this IP which is going to the design house, so some untrusted people in the design house can make illegal copies of the IP and avoid paying royalty. So again, as I mentioned, this is several $1 billion of business, so you do not want the illegal copies to be sold in the market because that's a big revenue loss for the IP vendor. Secondly, the design house can also modify the IP and sell it under different brand name. Again, this is another attempt to violate copyright. And finally, in the fabrication facility, there can be hackers or potential untrustworthy people who can manufacture illegal IC instances and sell it to the market, so that they again prevent paying loyalty to the design house. Or even post fabrication, once you purchase the IP or a hacker purchases the IP, they can reverse engineer the file. It can be done also during fabrication to find out, reverse engineer the IC to find out the design, underlying design, and modify or refabricate it so that again they violate the copyright law. So during this phase, a potential attacker can also insert hardware Trojan so that that Trojan after fabrication can cause disruptive functional behavior in the integrated circuit. So these are the snapshot. This is the snapshot of different modes of security threats we have in hardware or in electronics today. Now let's talk about hardware Trojan horse, and then we'll go to hardware intellectual property. Now what is hardware Trojan horse? Now typical combinational circuits will look like this. You have some inputs and outputs, and then you have a circuit which can be purely combinational, or it can have sequential elements like flip-flops in it. So a circuit can be considered as a black box where input is coming into it and output is being generated here. Now the fact is an attacker can insert a tiny circuit which can compose of just few gates, so that depending on the internal state of the circuit, it can cause malfunction or it can induce malicious behavior in another node, so that eventually the output would be affected. So your functional behavior would be disrupted. Now this is the combinational Trojan, where the Trojan circuit composes of only combinational logic gates like AND OR. Similarly, one can think about a sequential Trojan like a counter which will trigger a malicious effect into the circuit through long hours of operation. That means only when that circuit goes through a sequence of rare events, it can cause a malicious effect into the circuit. So that is very difficult to detect that effect during conventional testing, but during field operation, you can have that malicious effect. And interestingly, the Department of Defense is very much worried about this effect, because most of the ICs today are being fabricated overseas. And if it's fabricated overseas, it can have malicious effects introduced by an adversary. And these effects are like this. They can introduce a Trojan hardware or Trojan circuit inside the actual circuit, which is very, very difficult to detect after fabrication. So these are the examples of the circuit. This is a combinational Trojan example. This is a sequential Trojan example. And this is a system level Trojan example, where you can have the processor, the IP blocks like MPEG, RF, and USB. You can also have memory. And then the adversary can introduce a small Trojan circuit, which on condition of certain events on the bus can cause a wrong memory write, so that the state of the circuit will change and it will cause disruptive behavior. So the question is, how do you detect them? How do you detect Trojan? Now there are two broad categories of approaches. One is called destructive approach, another is non-destructive approach. In destructive approach, what you do, you tear open the hardware or IC and try to find out that the actual GDS matches with what is fabricated. Now that's very difficult approach and very expensive one. You cannot afford to do it all the time, because you fabricate millions of ICs and you really cannot go to the lab and basically put all of them under microscope and find out what's going inside that. So that's very expensive, and that's not really feasible approach for large scale IC fabrication. But what is more feasible is non-destructive approach. In non-destructive approach, what you do, you take the IC and do some testing on that based on electrical parameters. And this testing can be either logic testing or side channel testing. In logic testing, what you do, you give some inputs and try to find out what is the output. And if the output is not matching the expected output, then you have probably a Trojan inserted into the circuit. But this approach is again very difficult to make it successful, because the attacker will make sure that the Trojan is activated at only very rare condition, so that during testing it's very difficult to activate it and find it out. Another interesting approach which we are looking into actively is called side channel approach, where you basically monitor the side channel parameter like current or power signature, so that you can find out if something additional is there inside the IC. Now this is an effective approach, but of course there are some challenges. Let me list the challenges in two approaches. So this is the comparison in terms of advantages and disadvantages of these two non-destructive approaches. There are advantages for both approaches, and we believe that in order to make sure that all Trojans of different sizes, of different types can be detected, we need a combination of both approaches. And we are also looking into a combination of logic testing and side channel analysis for detecting any type of Trojan of any size. And we have also published some papers recently on our approaches. So these are the papers we have published. And again, as I mentioned, this is a new topic, so there are a lot of active researchers looking into these topics. And again, nobody has come out with a conclusive solution yet. But our vision is that we really need to have a combination of two types of Trojan detection approaches in order to make sure that we can detect all Trojans. So that's about hardware Trojan. Now let's talk about hardware IP. And as I mentioned, today's complex ICs are fabricated of or designed out of small modules, and these modules are called intellectual properties, and they are developed by third party in general, and they are sold by those third party vendors. And global hardware piracy today is estimated at $1 billion per day, which is a huge market, pirated market, and we really want to avoid that, to make sure that the vendors which really develop the IP, they do not have any revenue loss due to piracy. Now, this causes loss of market share, revenue, and reputation. It affects all parties, because if you have untrusted IPs, not only the IP vendors are affected, IC design houses, system designers, and even the end users will be affected, because now in the market you have untrusted copies which you do not know if they work well or not, or if they are tested or not. Now, what is our approach? What we are doing, we are trying to make sure that all parties involved in the design phase will have secure and trusted IPs. So what we have come up with is a technique which is recently published in this conference. This technique, we also have a corresponding, we have also have a previous publication of a technique which is similar to this in another conference here. So the technique is very simple. We have a locking mechanism. Like the software, like the password protection in software, we have a locking mechanism for IP. So what we do, we make sure that the IP will only work if you give a password, right? And this password is called enabling key. So how do you do that? You try to make sure that the state transition function of the design will go through a sequence of states. Unless you apply the correct sequence at the input, it will not enable normal behavior or normal operation. So that's the mechanism we have. And again, this is very well accepted locking mechanism. And we believe that we can pursue this route and make sure that we can assure security or trust for all parties involved. So there are a lot of open questions, as you mentioned. The first one is that can we achieve 100% trust of hardware using non-invasive, non-destructive approach? So how do you make sure that the ICs which are fabricated in untrusted foundries are trustable? Can you do that using some validation technique? Can you design electronic circuits that are Trojan proof? Can you come up with design techniques so that nobody can insert Trojan into it? So that it's very difficult to add any modification, malicious modification into it. The third question is, how do you verify hardware IPs from untrusted party? As I mentioned, the third-party vendors which are selling IPs may insert Trojan into it. So how do you verify that they are trustable? And finally, how do you protect IP during evaluation? So at software, the IPs should also have evaluation copy, and this evaluation copy can be again sold as clones, can be cloned or can be sold without paying royalty. So how do you make sure that you can protect the evaluation copies of IPs and also make sure that it's widely distributed so that you have good marketing of those IPs? So these are the open questions, and you do not have really answer. You're looking into them, and if you're interested, we'll be happy to talk about these things. And the answers, my friend, are blowing in the wind. And we have a lot of collaborations going on. Dr. Prapakristu, Francis Wolf, Dr. Kaushik Roy, and Dr. Anand Raghunathan. Okay, I'm out of my time. Any question, quick question, one or two? Okay, so I will pass it over to Dr. Luparo.
My name is Ken Luparo. I'm, of course, a faculty member in EECS. And what I wanted to do today is to just sort of share with you some of the research that I've been involved with, especially over maybe the last 5 to 6 years. The theme behind much of my research is the concept of complex systems and how to deal with complex systems both in engineering, healthcare, and the life sciences, and this whole notion of how systems methodology, signal processing, and control is actually horizontally cuts across all of the disciplines in engineering, healthcare, and the life sciences. And this term systems biology, which has been floating around for a number of years, I'd like to talk a little bit about what that is and how it relates to research at Case, and in particular, my own research. So first of all, it's important to sort of understand what we mean when we talk about complex systems. What are they? Well, one of the things that usually happens to involving most complex systems is that they're multi-level and hierarchical, which means that they could be spatially distributed, they could be temporally distributed, so they have behaviors that occur at both many spatial and temporal scales, plus they're organized in a multi-layer or hierarchical context. So you can think about social systems that are hierarchical. For example, the university, you got the president, then the provost and the dean and the department chairs. And then I'm not sure where the faculty and the students are, whether you're above us or we're above you. It really doesn't make any difference. We're down in the trenches anyways. And so that's where the rubber actually meets the road. So there are many systems that are multi-layer and hierarchical. But the thing that's interesting from my perspective is that I'm interested in systems that are also dynamic, that are evolving in time and require exchanges of information both within a given level, so between faculty and students at the same level, for example, between levels, between faculty, students, and the department chair, or the department chair and the dean, and up and down the hierarchy. And I'm interested in how you manage a complex, dynamic behavioral system of that type. What information do you collect? And once you've got that information, what are you going to do with it? How do you manage it? How do you control it? And so one of the things that has been of interest to me for a long time, probably since maybe the mid-'80s, before it was even popular, is this concept of hybrid systems, where there is an organization of the dynamics or of the behaviors that involves both continuous and discrete aspects. So that the fact is that you've got continuous and discrete variables, and I'll show you some examples both in terms of engineering systems and biological systems where this notion of hybrid dynamical systems is natural and actually fits the best to the problems that you're trying to solve. So one of the motivations for my work is that I started out as a theoretician, and so at that point I created problems that I knew how to solve. All right? I knew the mathematical machinery that I could apply, so I would look at problems, theorems, corollaries, and lemmas that actually I knew the machinery I had could be applied, and then you can write a paper and you move on your way. I realized pretty quickly that, in fact, the best way of developing theory is to have it from the top down rather than percolating from the bottom up. That is to make these problem-driven. So much of what I'm going to talk to you about today, even the theoretical work that I've been doing for the last close to 30 years, has been driven by problems that are of interest, and most systems that you would want to consider are of this hybrid or mixed type. They involve discrete states and continuous states, and they need to live harmoniously. Unfortunately, when they do live together, they generate very often very complex behaviors that you need to manage. So one of the things that happens in these multi-level or hierarchical systems is they're generally organized into modules or subsystems or subgroups, and these can be loosely connected or tightly connected. And if you look at an interesting biological system such as a cortical neural network, these are whole sets of individual dynamical systems, neurons, that are organized or connected through synaptic pathways. And sometimes their groups are tightly connected. In some disease states, they're way too tightly connected, and sometimes they're loosely connected. So it's important to understand these modules. These modules can be physical, they could be conceptual, and so you need to be able to deal with them, and they're dynamic. Different subsystems can form clusters at given points in time to solve certain problems and then do other things. Also, everything in my mind is probabilistic and stochastic. There's nothing certain in this world. And so being able to include probabilistic and stochastic attributes into the models, into the problems, into the decision making is absolutely essential. And then these systems can have multiple kinds of behaviors at various temporal and spatial scales. They have properties that are easy to say. They sort of roll off the tongue. They're adaptive. They're self-organizing, et cetera, et cetera. They're very difficult to do, very easy to say, but they also add degrees of complexity. And then there's decision making at multiple levels. And I want to, if you get nothing else out of what I'm going to say for the next 10 minutes, recognize that coordination and control are two distinct aspects. Coordination is trying to influence somebody to do something. Control is telling somebody what to do. And these are two different paradigms, and it's important that one understands the role of control as well as the role of coordination, and that these span multiple layers and multiple levels in a hierarchy. So one of the areas that I've been involved with since my graduate days I'm not going to tell you how old I am, so since my graduate days a long time ago, most of you probably weren't even born, is that I was been very interested in energy and the grid. And this is a subject that is very relevant these days. And in particular, as we look at how to move forward with reshaping the grid, everybody has heard stuff about smart grid and microgrids and grid-wise and all other kinds of ideas. The whole thing is that the grid, as it currently is organized, is not sustainable in terms of its infrastructure. Its infrastructure is collapsing. It has not seen the investment it needs to see in order that it is state of the art. But it's also, even though it's highly distributed, it's actually operated in a fairly centralized way. That is, the utilities control everything. They're responsible for all of the generation, more or less. They're responsible for transmission and distribution, and whatever happens at your end, at your house, you take what they give you. And in fact, if you could try an exercise, call up your local utility and ask them, how much power or how much energy am I using right now? They can't tell you. They have no idea. There's no understanding. They have no record of what you're doing until somebody comes out and reads the meter at the end of the month, and you get a bill. That's it. They have no other idea. No. And when there's a fault on the system and a line goes down, they have no idea that that line is down until, guess what? Till you call them and tell them, I don't have any electricity. Oh, where are you? Tell them where you are. Enough people call, they send out a truck. Go find out why Remo doesn't have any electricity. So the system, although highly reliable, is very, very deplete on the kinds of sensing and distributed control architectures that are necessary to support its evolution, especially as we start to add renewable generation to the system. The system cannot tolerate renewable generation at the levels that we're talking about right now. So what we've been doing is looking at a new concept called security-based analysis and control. And the key is based on modeling this grid system as a hybrid dynamical system, where one of the most interesting things about the grid is that the state of the system, voltages and currents and frequencies, and the structure of the system, what generators are connected, what lines are connected, what transmission and distribution pathways are active, are actually linked very, very tightly. So you can't talk about the state of the system without understanding the structure, and you can't talk about the structure without understanding the state. And this is something that that's new in the power system area, and we've been developing these models over a number of years and trying to impress essentially a finite state automata model at the highest level that actually is driven by dynamical systems at the lowest level, and that essentially the control problem is to maximize the probability that you're in the normal state. Okay? So it's a very, very intriguing and challenging problem, and it's quite relevant these days, and we're forming quite a group around these efforts. Another area that, since Farhad is here, another area that we've been interested in is ICU monitoring. And so when you're in the ICU, and hopefully you never have to be in the ICU, but if you are, you will appreciate the fact that there's a multimodality of instruments and sensors that are placed on the person being monitored. And the fact is that you're trying to react to multiple and complex pathophysiological events, and this is an attempt to manage the healthcare in the ICU. The problem is that most intensivists right now operate exactly on fly-by-sight. That is that all of this information that sits in the ICU appears on monitors that are scattered all around the ICU. There's no integrated or consistent way of interpreting or viewing this data. And so essentially, they're looking at all of these gauges and dials, intracranial pressure, EEG waveforms, all other kinds of physiological markers. And then based on this glimpse, okay, this is a glimpse. They look at these trends. They're going to decide what your state is and what needs to be done. So the idea, of course, is that you'd like, when they're critically ill, then essentially they're flying totally by the gauges because they can't interact with the patient at all. The only thing that they can do is to rely on the information that's coming off the monitor. They can't ask you, how do you feel? How are you doing? So everything now is essentially interpretation of the data. Unfortunately, if you look at a modern day ICU, this is exactly how it looks. There are all separate instruments all around the room. None of them communicate with each other. And they're all streaming data in a proprietary data format, which if you're not real clever, you can't even unravel. And all you can do is to look at the monitor as opposed to collect this data and integrate it and analyze it as you would as an engineer or a computer scientist. So the idea is that the current state of the art is that you've got a nurse in the ICU that does what? She looks at all the monitors and she writes down on a piece of paper what your heart rate is, what the intracranial pressure is, what your temperature is, and she writes that all on a piece of paper and then what? Sticks it in a chart. So then the next day comes by, the only thing they've got to look at is what's in the chart. All the rest of that data is not archived and completely disappears. So this is a slide from a friend of mine, Michael DiGiorgio, who says that what we're doing in the ICU, and he's an intensivist, so he can say this, it's exactly like what they used to do in the stock market back in the 20s and 30s with the ticker tapes. That is, essentially what we're doing is we've got all of this electronic data and fancy equipment and sensors, and here we are looking at taking that data, writing it down on a piece of paper, and then stretching it out and asking your colleagues to say, well, what do you think we should do with this person? So what we set out to do is to essentially take it into at least into the 1990s, and to look at how does one integrate this data in terms of multiple instruments through a data acquisition model, and then take that data and do some mining of that data and provide an intuitive interface for an intensivist so that they can see what's happening to a patient very clearly. Now I'm going to take 2 more minutes and talk a little bit about what we're doing in the life sciences in this concept of systems biology, since it may be something that you're interested in. My conception of systems biology is sort of outlined on this slide. And that is it's really a way of trying to understand how genes and genotypes, as well as the environment, which can include both positive and negative influences, all come together to generate a phenotype. What is a phenotype? A phenotype is something that a clinician looks at in terms of a particular disease. So hypertension is a phenotype. Sleep apnea is a phenotype. So what we're interested in is trying to understand how genetic endowment and genetic makeup, together with the environment, come together and provide a description of various types of phenotypes, diseases that we're interested in studying. And what we want to do is to look at integrating sort of this genetic information, which for the most part has been relegated to the titles of bioinformatics and computational genomics, and put that together in what we call a systems biology framework, where you integrate the genetic information with information on the environment, as well as physiological measurements that say something about the current state of the individual. And the whole idea is to find a way of better understanding the biology, better understanding of what you mean by health, and better understand what you mean by disease. And one would like to be able to develop strategies to maximize the probability of remaining healthy rather than simply waiting and detecting a disease after it occurred. And this is my last slide. Based on this systems biology concept, we have a number of programs that are going on. The slide on the left pretty much shows this sort of systems biology workflow where hypotheses are generated clinically, experiments are designed to try and confirm those hypotheses, data is gathered, the data is integrated, it's used in modeling, it's used in what we call in silico experiments, experiments in silicon. So these are just computational experiments. Information from those computations goes back up to modify the hypotheses. And so this is a multidisciplinary workflow involving clinicians, engineers, and basic scientists. What we've been doing is that we've been working in the Cancer Center for the last 5 years to understand genetic types of cancers, mismatch repair deficient cancers. I don't have enough time to talk to you about cancer initiation, but one thing that I can tell you, at one time they thought cancer was an event. That is, you didn't have cancer, then you do have cancer. Of course, that's not true. Cancer is a process. It's a process that evolves through initiation, through progression, ultimately to disease. So one needs to understand this dynamically, and most of these cancers are all tied up in the cell cycle because of the fact that these tumor cells need to replicate. They replicate during a DNA replication process. This is how they develop. So understanding the cell cycle and its characteristics is absolutely essential in order to say something about cancer. We've also been looking at other computational phenotypes in terms of EEG, as EEG complexity is a measure of neurodevelopment. We've been looking at variability in arousal patterns and hypertension, and we've been looking at information theory measures as it relates to respiratory and cardiac coupling and how that relates to cardiovascular disease. And with that, I took too much time. I will stop. If you have any questions at any time, I'd be happy to talk with you. Okay. Thanks, everybody.